Hello, I'm Oliver Gao. I am the director of Cornell System Engineering Program, and I have been doing this system conversation with our Ezra Systems seminar speakers. So today we are very delighted to have Professor Chris Iyer. Chris is an assistant professor in the School of Operations Research and Information Engineering at Cornell University. He is one of our own. His research interests include game theory, stochastic modeling, dynamic markets, and the mean field models. He's actually, he's the recipient of the Stanford Graduate Fellowship, a Ralph Watt 72 Excellence in Teaching Award, and the first prize in the 2017 Informed Junior Faculty Forum Paper Competition. Congratulations and welcome, Chris.
Thank you very much.
It's very great to have you here. So I can see that you have a very outstanding research track record as well as teaching record. So would you like to start by telling us more about yourself, your research, or whatever you would like our audience to know about you?
Yeah. I'm very glad to be a part, giving a talk at the system seminar today, and thank you very much for the invitation. So just a brief background. So I'm originally from India, and I did an undergraduate in mechanical engineering at Indian Institute of Technology, Bombay. From there, I sort of moved on from mechanical engineering into operations research and industrial engineering, and I came to Stanford University to do my PhD in the management science and engineering department. Subsequent to that, I did a short postdoc at University of Pennsylvania, and then after that, I joined Cornell in the ORI department here. So since my PhD, my main interest has been broadly in the area of game theory as applied to markets in particular. So in particular, I've been very interested in understanding dynamic settings where agents or players interact with each other over multiple time periods, and their actions across time periods are coupled in some form, right? And there are many examples in practice where such instances occur. So you can think of this as traders in a financial stock exchange who are trading over multiple time periods, maybe trying to execute a trade or trying to hedge a portfolio risk or things like that. Or more on the tech side, you will have companies like settings like online advertising, where advertisers try to bid on auctions for keywords or trying to show their ads on their website. And these auctions occur repeatedly during the course of the day, but they have budget constraints that span a particular campaign duration, ad campaign duration. And so settings like that have been particularly interesting to me. More recently, I've been focusing on the question of information design, like how do you design mechanisms that allow like maybe a service to share information about its service provider to share information about its service to incoming users so that they may decide to act in a certain way. Mm-hmm. So that is what I'm going to talk about today in more detail during my talk. Yeah.
You mentioned that actually you started in your undergraduate study, you were studying mechanical engineering.
Yeah.
And then you move on to management science and engineering. This is a very good example of people starting in the general engineering field, and then in their graduate study they kind of branch out broader. I feel like kind of from mechanical engineering to management science it's kind of more systems oriented. Okay. So how did you feel, and what was your motivation? Like usually, because one thing, and also you talk about your research related to game theory. So as I can imagine, as a mechanical engineer, you can look at, for example, a steel bars or some specific, the mechanics of a natural product or man-made product. It's a product. Yeah. However, now when you go to management science, you are dealing with the subjects of humans, where games. So how did you manage to bridge this gap and make this leap?
Yeah, so that's a very interesting question. And in some sense, at least from my perspective, it seemed like a more natural progression. So when I started, I was interested in mechanical engineering. I was in my, like, let's say, third year of my undergraduate. I studied about all these. How do you schedule jobs on a machine? So simple optimization mechanism, minimizing make span time, things like that, which sort of caught my interest. And I wanted to explore more about this in that context, like how do you manage operations in a factory and stuff like that. So over the course of time, I found that there was this area of industrial engineering and operations research that sort of tries to apply more mathematical approaches to sort of understanding this problem, in particular, how to model such problems in a meaningful and tractable way so that you can come up with some meaningful insights about how do you arrange your operations. And secondly, I think I found the math underneath it very beautiful. So that was also one of the attractions for me. And so from there, I started studying sort of problems that were not just static but more dynamic, like how do you do decision making, sequential decision making in when you have constraints on if you want to I don't know, schedule jobs on a machine, but you care about like your overall project completion time. So these processes are typically modeled using Markov decision processes. So I started learning about that. Constrained Markov decision process. That was in fact my master's thesis in mechanical engineering, and that sort of hooked me onto this whole area. And then I said, okay, why have only one decision maker? Why not if you have multiple decision maker? And sort of that got me into this game theory thing. So it was sort of a progression. So it was not like a jump from one to the other, but so now in some sense. Some of the results that we use can be used to study those kind of questions, like operations questions, in more broader settings. So although I feel like I'm in some sense not really moved away from what I've been doing ever since, but maybe in terms of labels, I've sort of moved away from mechanical engineering.
So you mentioned several times games, and then also like now you're doing research that will support like the market design or market development. So now, of course, the markets include games. So what's your view about the relationship between games versus market? What are the similarities and what are the key differences between these two terms, games and markets?
That's a very interesting question. From an economic perspective, I would say there isn't much. There is like markets are a type of like games among different participants, like buyers, sellers, these intermediaries, retailers, and so on. So you could say that games are sort of just more broad. It doesn't have to be a market like. But from a layman perspective, one way to think about this is usually when we talk about markets, we think about like there is some trade going on, maybe some there is a buyer and a seller, but there are many instances where at least traditionally you wouldn't call something a market, even though people are actually trading with each other. So I think that like, for example, you wouldn't call an organ donation system a market typically, or if people call organ donation a market, like then people find it repugnant. So that might be one difference between. So you can call it a game, I guess, and that the people are fine.
Yeah. Of course, I think one of the research, the recent research you're looking at the optimal information sharing. Yeah. And of course, the keyword is information. And we just talked about the relationship between games and the market. And what role does information play in either a game or in a market?
I think that's so, especially if you think about like over the past like couple of decades, where most like with the rise of Amazon, eBay, and all these online platforms where people can trade, there is in some sense, say if I'm a buyer and I want to go buy, let's say, an airline ticket. Typically, like I mean, I would have some flexibility of when I should buy. Should I buy it today, or should I wait for the prices to go down? Maybe the prices may not go down. I don't know these things, and in order to make my decision, I would need to sort of know what are the underlying ground facts, like how many seats are available and things like that. And these are information that I wouldn't have as a user. Whereas this is an information where an airline company or the platform that's selling airline tickets would have, right? How many seats are available. And so this informational asymmetry causes sort of like a tension, like the platform could choose to share this information with me in order to help me make my decision, right? But it doesn't have to reveal this information fully, or doesn't even have to reveal this information exactly, right? So so the question is like, how is there a way where platforms can strategically reveal information in order to influence my behavior so that it's more likely, let's say, I would buy when the price is high, if the platform only cares about revenues, let's say, right? Yeah. So you can think of this in more other settings which are maybe not really a market, but let's say if you are a road network and if I'm a driver and I have to choose which route to take to go to my destination, right? And before I make my decision, I wouldn't know what the congestion levels are in the different routes, but maybe a traffic operator does know this, right? And the traffic operator could exactly reveal these congestion information, but we know that if with exact information, there might be some, let's say, oscillations, or even like people might end up choosing sort of make decisions that are not efficient from the system perspective. Right? There might be more congestion than if you could optimally control the drivers, right? So one way the traffic operator could sort of balance this would be to not fully reveal the congestion thing. Maybe they could just say, this road is moderately congested, or without giving you exactly what your travel time would be, for example. And by giving these kind of vague information, it could happen that I might make a decision that is optimal from the system's perspective, even though it may not be optimal from my individual perspective, right? If I had actually known the information.
So far, like we talk about the games market, and information is playing such a critical role in determining the behavior of the individual in the system and also the ultimate equilibrium for the whole system. Yeah. So you'll be taking a mathematical approach to this. Yeah. And why a how, for example, can you give us some more example or some kind of in-depth discussion how you used your advanced mathematical tools to review some system phenomena that, without the help of the math, we wouldn't be able to either predict or discover that kind of phenomena so that we can take actions ahead of time.
So one approach we could take is to say, like, one of the main advantage about taking a more mathematical approach is to sort of, you can exactly, at least in one clean model, you can exactly investigate how different players in the game would react to certain changes in the model. Like, what if you did this instead of that? What if you increase the price? Things like that, right? Mm-hmm. We could take a more sort of either an empirical approach where we could study how let's say drivers are actually behaving in roads, how do they make their decisions, and then come up with it. But that in some sense would be harder to come up with counterfactual arguments about how they would have reacted if you had done something else, right? Whereas if you if your model is more like starts off with a more like modeling from the sort of what are called like micro foundations, like how do you model, how do customers make decisions, let's say, or how do drivers make decisions, then it would be easier to study the equilibrium of the underlying game and ask, like, if I change something, the game changes, and then how does the equilibrium performance change, right? Now, of course, this is not, I would not say like this is better than the other one and so on. Obviously, we will have a mathematical model, and you want to actually study whether this is actually captures whatever is actually present in reality. So there would be work needed to do to sort of either calibrate this model or validate the model. So I wouldn't say like one is one, like you need both approaches to sort of understand what is truly under the ground truth in some sense, right? Mm-hmm. So I have been more focused on trying to develop models to capture various phenomenon, but the other part is something that I'm quite interested about too. Yeah.
I think probably majority of your work you are trying to achieve optimality in either information sharing or some mechanism in distributing this kind of information. So, for example, you talk about this optimal information sharing in an unobservable single queue. And also, I think you said that, in general, you said that the optimal signaling mechanism requires the service provider to strategically even conceal the information in order to incentivize the customer so that you can achieve the optimal objective that the system manager has in mind. Yeah. So, but do you really believe in such kind of optimality?
Yeah. So, so one thing is that, I mean, so although we study optimal mechanism, we show that there is a huge gap between the optimal mechanism and something like just revealing all the information or hiding all the information. Mm-hmm. So even though in practice, you may have other concerns, like not just maximizing revenue or not just, you may have other concerns and you may not want to go up to optimality, but this work shows that you can actually do something in between. Like you don't have to, this is one of the tools that a service provider or a platform has with which it can control the system performance, right? Mm-hmm. So information is a commodity or is a resource that the platform has that users don't have. And that is something that a platform should be thinking about how to share that with its users, right? It should be a decision that is made consciously, right? How much to share and so on. And this is a very new area in some sense, like there are people it's like 4 or 5 years old. So there is still a lot of work to be done about like what if there are you are interacting over a long period of time, what if you have multiple objectives, how to do it. So this is sort of you could say like a first step towards that direction.
So when we talk about like information sharing or distribution to the users of a system, right, you design this such mechanism, and then so how does the quality of the information affect the mechanism that you design to distribute such information? For example, like one of your colleagues, Jamal, he was looking at this when we distribute this like travel time information to the users. However, if your travel time itself actually has not only uncertainty but so it's delayed or something, and then that could actually end up with a system that is not intended for. Yeah. So how does the quality of information affect the mechanism for distributing information and also the outcome for the system?
Yeah, so that's a very good point. And so in my model, I assume that, like in my work until now, I assume that the service provider in some sense knows the true underlying uncertainty. Anything that the service provider does not know is something that is not important for the user's decision. So, right. So, for example, if I'm thinking about the queue, the service provider knows how many people there are in the queue, but they doesn't know exactly how long they will take for service completion. Right. So it's a good question, like what if the service provider themselves did not have all the information that is useful for the players or the customers, right? And there have been some recent work that sort of study this problem, right? But I would still say that the framework that we develop can still be applied to those settings, right? It's just what we obtain at the end is some optimization problem that the service provider has to solve in order to find the optimal mechanism, right? And if your information is not perfect, you have some imperfect information, then the set over which you're optimizing has more constraints. It's a reduced set in some sense. But you can still apply standard optimization methods to find the optimal mechanism.
I see. So does your model also take into account, for example, it's in the game and one stakeholder has information and distributing this information probably to either another individual stakeholder or another group of users, right? So you're designing such kind of mechanisms. So I assume that, like for example, if you are the designer or you have a power, more power in this game, and you collect information, you distribute information according to your objective function. That could be for a company, that could be maximize the profit, right? And then the users, customers, right? They will probably, when the information is distributed, they will just take it. You probably make money, but the users, they're going to learn. So they're going to learn from this dynamic process. So how does the dynamic interaction among the different stakeholders, or how does your optimal distribution mechanism evolve according to the interactions?
So that's a good point. So in particular, that is something that we want to capture in our model, right? So in particular, we do like the fact that the model that we are looking at is the framework that we are looking at sort of assumes that the customers will respond to however I'm going to share information. So and in fact, we can show that fact is what allows the service provider to use information to improve system performance, let's say, right? So in particular, for example, if I even when the system was busy, I keep saying that system is free. In equilibrium, customers will realize that you keep giving me wrong information, right? Whenever you tell me system is free, there is some chance that the system is actually busy, right? So we actually modeled this sort of evolution of the agent's beliefs in the model, right? So in equilibrium, the agents would sort of not believe what you're saying if you start giving information in a particular way, right? So, and given that my behavior would not be just to blindly follow whatever you say, it would be just given what information you give me, I will sort of reason that, okay, maybe this information was right, maybe this information was not wrong. There is some chance of each of these events to happen. Based on that, what is my optimal action, right? So now you as a platform would know that I respond to however you give information in this more rational way, right? And hence, you will try to give an information that is not too wrong in some sense, right? So that affects how you share information in the system, right? So we do model the fact that the agent's beliefs must come out of this sort of iterative procedure where, like, if you act in a certain way, I will, from my past experience, I will realize that you are acting in this way.
This research, I think I can see how powerful it is when it's going to be applied to the real world. So imagine, like here, I have the transportation background. Imagine, for example, this kind of Uber service, right? And that's, of course, customers using service that they are going to be in the queue, right? Probably their behavior or also decision will probably mostly be affected by the pricing strategy of the Uber platform. So now imagine that, in this Uber like mobility market, I can see three like players, three groups of players. One, of course, it's Uber itself, right? Uber can certainly use your model, right? They think about what kind of information and using what mechanism to distribute to what groups of users, right? So now imagine if I'm Uber, and how can I take the full advantage of the research you have done?
Yeah, so of course the Uber's problem is much more general. There are multiple places spread out across the whole city, and people are asking for rides all over the place. So our model is sort of like capturing maybe say one location and trying to understand how information sharing should happen in that location. Right?
That's right.
And of course, subsequent work could be sort of used to do this to a more sort of broader setting where you have multiple regions where people are requesting rides and so on, right? And just to sort of sort of the motivating example that we use is like if you are a rider and you have an option between either taking an Uber or maybe taking a taxi or some other public transport, right? And you want to make this decision based on how long you will have to wait for a rider to come and pick you up, right? And this is something you would not know unless Uber tells you, right? Because that's information you can't see, you don't know where the Uber drivers are and so on, right? So again, our model can be used to sort of study like how should Uber share information about, let's say, wait times for pickup to people who request rides, so that they are more likely to wait for the Uber driver rather than maybe take a public transport or take a taxi that's just waiting there, right? You mentioned that there are three stakeholders in that setting. Like at least currently, if you think about it, the Uber already seems to be doing some amount of like I don't know if it's an optimization, but at least some strategic decision about how to share information. So if you are a user, if you open Uber's app, you can see how many Uber drivers are around in your location, or maybe get a sense of it. You can see it on your app. Whereas if you're an Uber driver and you open the Uber's driver app, that information is not provided by Uber to drivers, which is something that Uber has, right? But it is not shared with the drivers. So they are making some strategic decisions there. And the question is, of course, I don't know what objectives they are trying to maximize, but we could use this sort of framework of information design to sort of formulate that and try to understand what would happen if you changed this or if you provided some vaguer information and so on.
So now, assuming that, imagine like a Uber user, as sophisticated as, for example, or as kind of equipped as you are familiar with all these things. You know that Uber is designing this system like this.
Yeah.
And you as a user, how would you make your choice then?
Yeah, so presumably the framework captures that fact, right? The fact that if I give information, the users will respond accordingly. So we already model that in our framework, right? So if we didn't do that, right, you're right that user behavior will change and will not be what you would expect it to be, right? So if we just said like Uber should always say that the wait times are very low, right? Then I will say I'll stop believing whatever information Uber is giving me, right? So we show that it is never optimal for you to, in some sense, lie about what the system state is to a certain degree, right? So you may want to give less information than what you have, but you wouldn't ever lie about it, right? So if the system is moderately busy, or if its system is busy, you could say, like, if the wait time is, let's say, 10 minutes, it might be optimal for you to say that wait time is at least 5 minutes rather than actually giving a number, right? Or it is at most 12 minutes or something, right? But you would never say that when that wait time is 5 minutes, it never makes sense for you to say the wait time is only 1 minute, for example, right?
You're right. I believe, like for Uber, after they take into account, Uber or some other like service providers, after taking into account the user's responses, and they can design their information sharing mechanism such that they can achieve their goal. For example, I assume that for most of the companies or industry sector, their objective is to maximize their profit.
Yeah.
So now I have a related question. So imagine that here, because for example, if this company is so dominant in the market, such that the strategy this company is using can pretty much determine the ultimate equilibrium and also the reality of this whole system. Yeah. So in that case, so basically, me as a service provider, because the action I'm taking determines the reality, and I tell people the reality. I'm not lying, right? So which means this is. However, what if, for example, my objective function, because of my objective, I have driven the system to a state where it's a reality, but it's not good for the other stakeholder. Yeah. So in that case, for example, if now the third stakeholder, the government, the regulator, comes in, assume that they use your model, they can predict, for example, the company's behavior, like this, how the government can use your model to regulate.
Yeah, so that's a good question. One question might be like, what if there is a regulatory framework that says that you cannot give false information to users? Maybe am I understanding that correctly? Maybe.
No, it's not actually. The government doesn't. So can government regulate the objective function?
Yeah, that's true. So it could be. I mean, I would assume that it could be that there are some instances where if you just look at blindly optimizing your profit, then it might make sense for you to give information where you truly know that, let's say, this is probably not a good time for this user to use the system, right? But you still want, in order to make more revenue or profit, you tell them to like go ahead and use, and that's what the optimal information mechanism does, suppose, right? Yeah. And then over a long time, it could turn out that users realize this and they want some kind of protection from being sort of taken for advantage of in this way, right? And their one approach would definitely be that to impose some kind of a regulatory framework where they say that the quality of information that is shared must be within some limits, in the sense, maybe if you're sharing wait times, let's say, the deviation from the truth can't be too much, things like that. And that would, from the model perspective, from the framework perspective, that would only add more constraints on what information mechanisms are feasible, right? So right now our framework considers all possible information mechanisms, so we actually characterize a way to sort of capture that, right? And if you add more restrictions, like some regulatory framework, this will sort of put more constraints on what information mechanisms are feasible and what are not, right? And that would indeed affect how firms choose their information sharing mechanism. And that's an interesting question. I don't know if anybody has studied like what is the overall effect of such regulatory framework on the system.
Yeah, that's right. It's kind of probably, my question probably was more on how your model can help the regulators to become more smart, to become smarter. Because otherwise, I think we all know, like when the government has the regulation and industry, they can always play out of it. They can trick, right? So how can your model of imagine, for example, a company hires you or adopts your work and then in the meantime, if the government come to seek your help in designing a mechanism to achieve certain kind of more like government's objectives.
So in some sense, in the more public domain, like one question that pops up is sort of like these kind of public goods provision problem, right? So like how do you get some stakeholders to contribute money for some public project, right? And typically there you have these sort of free rider problem, and like you have people who don't want to contribute because others are contributing and things like that, right? And there maybe the government or the public entity there knows about who is willing to contribute and who is not willing to contribute, which the people involved probably do not know, or the firms involved don't know. And that, again, our framework can be used to study those kind of problems where they are strategically sharing information about, let's say, how much contribution has been pledged for this project, things like that, to entice more people to contribute and increase the total contribution, right? So that is one area in a more sort of this setting, but that still in some sense does not answer like how a regulatory framework can be applied here, but that is something that I haven't paid much thought of to, but yeah, maybe that's an interesting question to study.
We talk about this optimal information sharing, and then so how does the various level of power distribution among the stakeholders affect the optimal mechanism for information sharing?
So the question we are talking about is information sharing, right? So there is some underlying system that is evolving over time, and you could model different power differential among stakeholders or players by saying that the actions that different people take can affect the evolution of the system in different manner, right? So so our framework allows for all of that, right? And of course, the person who has more information stands to gain more out of such information sharing mechanisms, right? So right now, we are sort of, I would say, in the more early stages of this line of work where most of the work that have been studied are like you have one principal or one service provider who has additional information and maybe one or more agents that are trying to take some actions. And typically all of these agents are in some sense have the same effect on the system, right? But that is not a big constraint. You can have few players taking this thing. So obviously the questions now ask a sort of more information design question would be like, what if there were multiple principles that are all trying to share information and affect each other's behavior? But that is something that is like, I'm sure will sort of work in the next few years, some models where we can study those questions.
So in that case, imagine like kind of, I'm thinking in the context of nowadays, this kind of social media, right? It's not only, of course, imagine, there was this management center distributing information to all these different individuals. And these are different, I'm more thinking about this kind of learning dynamics. So probably, this individual first figure out the trick. This manager is playing. And then I understand that because of social media, and he can spread this, what he's learned very quickly. And how does today's technology and the social media and even kind of this kind of the crowd source of crowd sharing, how that kind of setting, or how would your model or your result apply to this kind of setting?
Yeah, so that is a very good question. Like actually people are right now, there are people who are studying these problems, like in a very basic setting, maybe sticking with the whole queuing setting, like what if when customers come in, they can maybe tweet about or post about how long they had to wait, that other people can look at to decide whether to come to the queue or not, right? So these kind of questions people have been starting to explore. I think there is a recent paper there where people talk about how does sort of these kind of information sharing among the users affect system performance, right? And then there are results. They have some preliminary results where they show that there are instances where such kind of sharing among users of a system could actually hurt the system performance, could maybe make the wait times longer, things like that. So, but again, this is a pretty active area that people have been talking about. Another sort of context that people have been looking at is like these kind of sharing of articles on a social media like Facebook or something. Like people share something which they themselves are not completely sure about whether it is true or not, this fake news and so on. And how does sharing that information affect its in some sense credibility? Like if you see a article shared by your friend, you might believe it more and you might be more willing to share it. And can these platforms do something to sort of prevent sharing of false news in some sense? So that's something that people have been actually studying pretty recently, like a few papers
really?
Coming out. Yeah.
I know like your work is very, it's a model that can be generally used in a lot of different applications. But if you were to choose or think what kind of application, real world application, that you'll be so excited and looking forward to for your model to be adopted in those kind of real world applications.
Like I said, I mean, the motivation for this was sort of like a ride sharing setting where like how do riders make this choice and how can you share information? So we have a very basic model for a single location in some sense, right? It would be interesting to study how this can be ported to a larger setting where like you could sort of coordinate about the information shared in different locations and riders in different location, right? And you could also think of information sharing in terms of in many contexts in that setting, like how do you pool users together, maybe by you don't exactly reveal how far you will have to deviate from your intended route, and that might help more people to go for the pooling option, right? And maybe that will reduce congestion on roads more. So these are questions that I'm pretty excited about and would be interesting to study.
This information sharing or information distribution, imagine in a situation of emergency evacuation, right? When they're happening in Hurricane Harvey, and then, so how can we use your model to decide the information sharing or distribution stage such that we can achieve, for example, that we can best achieve the evacuation goal. So for example, we know that, this is coming. And if we distribute the information to all the population, and everybody is going to hit on the road, that could slow things down. So just based on your kind of intuition, what would be a good strategic scheme for information distribution for situations like evacuation?
Yeah, so that is a good question, and that is sort of ties to some recent work that have been happening about like how do you share information to a group of users. And there are one way you could do what is called a public signaling, which is like you just make announcement that everybody can hear, right? Or you can do private signaling, like you give information to some groups and don't give information to other groups, right? So typically the private signaling is much more powerful than public signaling, and I would assume that in those settings, like you would not want to give this information immediately to everyone, right? So that doesn't cause congestion or something, right? Of course, in a more emergency kind of a setting, you have these concerns about information leakage, where like if I give some information to one people, typically like that will spread like wildfire. So it's a question of like how do you whether such mechanisms are feasible and how do you account for that. That is something that is so you need to model like how do people share information among themselves and so on, right? More sort of broadly speaking, like at a higher level, it just says like in order to sort of manage congestion and so on, it's a question of like you could tell people to take different, let's say, routes to get out of a particular location if that is your goal, right? And you can use your information sharing mechanism to tell them, to direct them in a particular way that is more closer to what you could have done if you could actually control them, right? You can actually tell them you should take this route, you should take that route. Obviously that is not feasible, but information sharing will allow you to come closer to that goal.
That's great.
Yeah.
Thank you, Chris. I think our time is up. I think this is great.
Yeah. Thank you very much, Oliver, for this opportunity. Yeah.
Thank you.